Hello and welcome to Lecture 17, covering Section 6.1 from Survey 11th edition on the topic of linear momentum and impulse. All right, so this is very much an introductory section, an introductory lecture, just to lay the basics of the definitions of momentum and impulse and do some hopefully simple problems to illustrate those definitions. Okay, so let's get right into it. All right, so we got some key terms. We should define what the heck momentum is, and then impulse. Okay, so first of all, what is momentum? It's a vector quantity, okay, of motion equal to mass times velocity. All right, so it's a new player in the discussion of motion. I'd say it's the final kind of new idea, really, because we've got energy so far, we've got the kinematics, and now we've got momentum. All right, I know it's like I always say this. I really feel like, why do we need momentum? But hopefully that will become obvious that there really is. It's not just useless. There's a reason that it's made its way forward as a staple of modern physics, or at least modern physics textbooks, Okay, but it's a vector, and I think that we should remember that because that's definitely going to distinguish it from kinetic energy. All right, so unlike inertia, right, because those terms get interchanged in everyday language. Oh, something has momentum, something has inertia, right? It only moving objects have it. Since velocity is used in this calculation, if you have zero velocity, you have zero momentum. You always have inertia because inertia is a property of matter, okay? Unlike kinetic energy, momentum is a vector. It's got direction, right? It can have components and so on. Okay? Momentum is also known as translational momentum. That's going to become more important when we talk about the other type of momentum, which is rotational momentum. Okay? So for now, I can basically just always call it momentum, but technically it's translational momentum, which is to say it's momentum where if we zoom in on that motion, it's moving in a straight line. Even if it's a arced path, if you zoom in enough, it can be described as a straight line. In other words, it's motion in x and y as opposed to purely rotation about a fixed point. But we haven't talked about rotation yet, so don't worry about it. Okay? So here's our other key term: impulse. Well, impulse is kind of funny. Is just force multiplied by time. That's it, right? So kind of like momentum is mass times time, impulse is force times time. I mean, maybe that's not so funny. We talked about work, right? What was work? Work was force times distance. So kind of, if you're sitting there, you're like, well, if I'm going to multiply force times distance, I might as well multiply force times time, right? Like, why not? Give it a try, okay? And it also turns out that by definition, impulse is actually the change in momentum. So that's interesting, right? So impulse is two things at once. It's force times time, and it's also delta momentum. Okay. Furthermore, it's also a vector, all right? So it does have direction and components and all that, okay? So let's get into the equations here. So here is momentum. Okay, here's a momentum vector. We can see the vector notation, all right? So its units are kilogram meters per second. I will generally, almost exclusively, refer to it as Newton seconds, okay? And you can see why it's a Newton second because a Newton is a kilogram meter per second squared. So if you multiply by a second, to cancel out the square, you get yourself momentum, hence the term Newton second. And it rolls off the tongue more than kilogram meter per second. Okay, so there it is. We represent it by the letter P, okay? So it's always, and it's going to be lowercase p in most cases, unlike power, which is uppercase P, but sometimes it can be uppercase P. I say the more important thing is the context, and also if it's ever a vector, it's not power because power is a scalar. And usually it's clear which is which, okay? But P is for momentum, all right? And there's the mass, and there's the velocity, okay? So we can see momentum is always parallel to velocity, always, okay? In the same way that force is always parallel to acceleration, okay? Now, speaking of force being parallel to acceleration, which is, Newton's second law, right? Remember this one? Okay? Well, it turns out that we're going to see Newton's second law again, okay? So this is Newton's second law in momentum form. All right. I never, called attention to that before when I introduced Newton's second law the first time. I just said, oh, here's Newton's second law, and it was F equals ma. But that would be Newton's second law in acceleration form. This is it in momentum form. All right. So it turns out that net force is equal to the change in momentum over the change in time as the change in time approaches zero. Okay. So this is technically a derivative, but we don't discuss derivatives in the class. So here we can just think of it as really, really small changes in time. So it's basically net force is equal to the change in momentum over time as that change becomes instantaneous, okay? All right, so if this is really Newton's second law, then it should also be ma, so let's show that. So let's get this. So all I'm doing now is I'm just rewriting momentum as delta mv, because after all, that is the definition of momentum, mass times velocity. And then I'm just going to pull the m out because the m isn't changing, right? M is not time dependent, okay? At least not here. There is an optional chapter where we actually talk about time dependent mass, which is honestly a cool thing about momentum, that we can tackle that in a way that we couldn't with our tools before. But we can't cover all the optional sections of the book. So you'll explicitly see that my notes do not cover it, which means you're not responsible for it. It's called rocket propulsion, and it's not covered in this class. Okay, so important thing being, the mass comes out because it's not time dependent. So anyway, then this right here just becomes ma, right? Because look at it, this is actually just the definition of acceleration. We've seen that before, right? It's the change in velocity over time as that time becomes infinitesimally small, ma. All right, so that's it. So it's Newton's second law after all. This is, the momentum form of it. Okay, cool. All right, so here, next one is impulse. All right, as far as logical letters, we should probably represent impulse as a J, right? That makes sense. Well, we do. Right, the units are Newton seconds, the same units as momentum. Okay, now, to be fair, that can happen sometimes. You can have different physical quantities at the same units, but there's a really direct reason why impulse has the same units of momentum. We'll get to it. But here it is, it's force times time, right? So it's force times a change in time, okay? Well, impulse, kind of, it's not like this one can't be a vector, but really most of the time you're going to see it as a vector. Well, look what it is. It is just change in momentum. So impulse is, yeah, sure, it's force times time, but if you think about it, if I take force times time, that's just multiplying both sides of the equation above by delta t, isn't it? Well, that would just give me delta p equals F times delta t. Well, F times delta t is the definition of impulse, which means an impulse must also just be, well, delta p, the change in momentum. Okay? So I guess I'm change in momentum. I guess I'm sort of saying that in a tongue-in-cheek way because it is odd, in some respects, to have a unit or a variable, really, called impulse, represented by the letter J and all, that is a change in something. We don't typically give a name to that. I mean, it's not like we call change in velocity, velocipulse, a velociraptor. But it's just that there's it's kind of, since it is force times time, it kind of stands on its own. It's a quantity that is helpful in certain situations, but it is honestly just change in momentum. Okay. All right, which also happens to be force times time, since the Newton's second law says it is. Okay, but I think you get the point. I won't go on about it. So the last thing that we're really going to see as introductory ideas of momentum is thinking about how it applies to a particular situation, which would be like collisions with a fluid. So let me show you what I mean. Okay, so here we have average force, and and we can talk about average force as far as impulse as well. But here I really want to make sure it's average. And this n here, all right, so this is a little kind of mini derivation here. This n represents the number of particles changing momentum. So this would be, something like a bunch of individual particles crashing into something, and each of them changing their momentum, changing their mass times velocity. Okay, so that's what the n is here. N is, there's no units or anything. It's just an integer that represents the number of something. And then we just have the delta t over the delta p, right? Because after all, force is delta p over delta t. Okay, at least average force. That's how, by the way, we were able to get rid of the limit, by talking about the average. Okay, and the negative is because of the directionality. Think Newton's third law. Okay, so then we can then rewrite that, because we'll just go ahead like we did above, up here that is, rewrite our change momentum, our delta p, as m delta v. Okay, and there's no delta, no change. The delta, of course, represents change. No change on the m because it's not changing. All right, except it can be if we group it with an n. So I'm not like contradicting what I said before. We're not going to talk about rockets, which are a very changing mass system, but we are kind of going to talk about something that has changing mass, but in a much, much simpler way, because n times m would be like summing mass. Okay, and so when we do that, when we take n times m, it becomes delta m. So in other words, delta m is n times m, because it's the number of something times the mass of each of those things. So then as you continue to count them, that's like a change. It's growing, okay? And so then the rate at which it's growing, the change in mass over the change in time, is the mass flow rate. All right, and that flow is kind of a giveaway, right? So that's the real utility of this version of the momentum version of Newton's second law, is that this is useful for things that flow. So it's applicable to fluid collisions like rain, water, or wind, where there's like an individual number of particles for rain, or there's just a mass per time for like rushing water. All right? And so then that way you can discuss something that is exerting a force based on the change in momentum of the flowing liquid or fluid. Okay? And we'll see one example of that, so it'll become more concrete if it's confusing. Okay? All right, well, let's get to those examples. So we got all fairly simple ideas here. You can see two of them I think are honestly simple problems, and I try to be honest about that. So type 1, simple problems that involve using the definition of momentum. Okay, that does in fact sound simple. Type 2, simple problems that involve using the definition of impulse. Okay, that would be the force times delta t. Also the fact that impulse is equal to change in momentum delta p. And then finally, problems that involve a fluid impacting a solid surface and exerting a force on that surface via the change in momentum of the fluid. It's a mouthful, but that's basically just using that last equation. Okay? All right, so let's get to it. Example 1. All right, so a 2.5 kilogram stone is released from rest and falls towards the earth with negligible drag. What is the stone's momentum after 7.5 seconds? So this is free fall, just plain old free fall, something that's probably becoming kind of familiar, an idea that maybe has sunk in. You're like, oh, I know free fall, right? So you use free fall kinematics to find V. All right, so here we have it. All right, this obviously is going to become minus G, but here I wrote it as more general kinematics. All right, so we'll plug in our specific values. All right, so we're trying to find the final velocity. We know it started from rest, so V naught was 0. We know we have gravity. All right, and y plus actually. Well, because I went ahead and just defined it as, well, here, more like this. I defined positive y as downwards, because there's not really, in this problem, there's no real reason not to, as long as, there's not much going on here. We just want a value. All right, so I'm saying, okay, well, sure, we're calling positive y down. Okay, so then we got gravity. And we have the time that we're given, 7.5 seconds of free fall. So then after falling for that long, it's moving at 73.5 meters per second downward, right? So I'm acknowledging that it's down, right? Since I called it plus. Okay? And then we're just going to find the momentum, right? Because we were talking about a 2.5 kilogram stone. And this would be no different than, say, like finding the kinetic energy or something, right? So we just multiply the m by the v that we found via kinematics. And there we go. The momentum of that object after being in free fall for 7.5 seconds without drag is 184 Newton seconds. And since momentum is a vector, we should specify that momentum points down, the same direction as velocity. Okay? All right. So definitely just the definition. This one is it's hard sometimes initially to know how to solve this one. But once you see it, it's a simple idea and it's kind of clever. All right. So we got a graph. By the way, we should always, with a graph, talk about the axes, right? We got a vertical axis, which is momentum, all right? Here you are defined in base units. I know I like to define it in Newton seconds, but here it's defined in base units. And on a horizontal axis is just time with units of seconds, okay? We have a 0 down here in time, which corresponds to a P1. So P1 is actually like final momentum, all right? Or at least momentum at some time greater than initial. And then up here is P naught. This is like initial momentum. So notice that P is kind of measured backwards. Or another way to think about it is that the initial momentum is greatest and then it falls off. So the momentum is decreasing. Okay? Well, that would make sense. In lots of situations, momentum could be decreasing. I mean, up here, we found that the momentum was increasing because initially it started from rest. So the initial momentum of our falling stone would be 0 because if V is 0, momentum is 0. And it's growing as it falls. But what if I threw something up? If I threw something upward, the momentum would start large and gradually decrease. Well, that's in fact what's happening here. All right, so we have, in example 2 that is, at time t equals 0, a ball is struck at ground level and sent over level ground. The momentum p versus time graph during flight is shown below with p naught equaling 6 Newton seconds. All right, so we're actually given the value there. We're told this value corresponds to 6 Newton seconds, okay? And p1 is 4, all right, down here is 4. Okay, so that means that this must be, if this is 6 up here and this is 4 down here, then this one's 5 and this one is, this would be 4.5 and then this one would be 5.5. Okay, so each of these is half of a Newton second. Okay, each division. At what initial angle must the ball have been launched? Oh, so we're going to get that all from this graph. All right, so just from the shape of this graph and from these values, we can determine that this striking of the ball is a projectile motion, because otherwise it wouldn't have the shape. Okay? Let's see. All right, so it's going to look something like this. The picture's going to help make sense of it. So initially there's some initial velocity, okay? And then at the top, there's a top velocity, which is the minimum, right? Because that's the shortest the velocity vector will ever get at the peak of the projectile motion. And that must correspond to the smallest value, p1 of momentum. It must, all right? Because that's clearly the smallest momentum gets, because then it starts growing again, parabolically, all right? And we also know that this wasn't tossing something straight up and having it come straight back down, because otherwise the momentum would zero out. And the minimum momentum was not 0, it was 4. Okay, so that's how we knew it wasn't a straight up toss. It had to be an angled toss at some angle theta. Okay, all right, well, let's find that angle. Okay, so what do we know? All right, well, we know cosine theta, right? Let's go right to our right triangle, is V naught x over V naught. Okay, fair enough. Okay, and V naught x we know is V1. Notice I'm using that subscript 1. You'll see why. All right, because it happens to correspond to P1. Okay, all right, and that's okay because since there's no drag, the horizontal component of the velocity doesn't change. Okay, and then since this is the smallest velocity, it must also be the smallest momentum. Momentum related to the velocity, or rather velocity related to momentum, is just momentum over mass. So using the definition, all right? And then meanwhile, our initial velocity, the hypotenuse, right, is the initial momentum divided by mass, which means the masses cancel, okay, which weren't given in the problem. And then we can say, okay, well, we know P1 and P naught. And then we could just isolate for theta, use cosine inverse, plug in our numbers, and it's 48.2 degrees, right? So this graph actually had enough information to tell us the launch angle, which is pretty neat, right? Like I said, clever, but once you see how it works, there's not many steps to it. Okay, so let's do a problem that involves the definition of impulse. Example 3, a force is provided to a golf ball at rest with a mass of 140 grams through the contact of a golf club. The force is constant and has a magnitude of 910 newtons. If the force is provided over 45 milliseconds, not very long, how much does the momentum of the ball change? How fast is the golf ball traveling after the force is applied? And how much kinetic energy does the ball gain? Okay, so in each of the questions, B and C will follow from A. All right, so first of all, we'll write down the definition of impulse. This is definitely one where we want to kind of consider both definitions, force times delta time and delta P, all right? Okay, so we're given the force and we're given the time, so that's the impulse right there, okay? Now, we actually weren't asked for the impulse. Numerically, if we wanted to find it, it would just be 910 times 4.5 times 10 to the negative 3. That would be the actual impulse, okay? And sometimes that's a number you want to report. But here we actually want to relate it to delta P because we're asked for the final momentum, all right? Or actually we're asked for how much it changes. Yep, so we're actually explicitly going to solve for that, which is, by the way, just the same as solving for J. All right, so it ends up being 41 newton seconds, okay? All right, and then how fast is the golf ball traveling after the force is applied? Okay, well, now I'm going to rewrite delta P as this P final minus P initial, because, of course, that's what a delta means, all right? And my P initial is 0 because the golf ball started from rest, all right? So then my delta P is just going to be equal to the mass of the ball times V final, which means that V final is just going to be my impulse, in other words, my delta P, my change of momentum, divided by the mass, 293 meters per second. That is the final velocity of the ball in regards to the impact with the club, and the initial velocity of the ball in regards to its subsequent projectile motion. Okay? Cool. And then kinetic energy, how much kinetic energy does the ball gain? All right, well, that's just going to be 1/2 m times v final squared. And again, the final is reference to the impact. All right, plug in all the numbers that we already know, right? This one was given, this one we found in part B. All right, and it's 6,000 joules. Nice round number. Cool. All right, hopefully that makes sense. Okay, so we just got a couple more. So this example 4 kind of ties in with question 1. These are really both kind of concept questions, but one of them is an example because it's numerical. The other one is entirely just doesn't have numbers, so it's better as a concept question, hence why I call it question. But what these two problems do, and together, they really highlight graphically how we can relate force and time, okay, or momentum and time. All right, so let's look at how it makes sense of this, because they're two sides of the same coin. All right, so let's get to it. Example 4. Okay, so the question is, what is the impulse provided by each of the forces shown on the graph below? All right, so Since impulse is force times time, it is the area under a graph of force versus time, right? Because the units have to be Newton seconds, and if this shaded area, for example, would have units of Newton seconds, wouldn't it? Have to, because it's an area. Okay, so that's the idea. The area under a force versus time graph is impulse. That's it. It's also change of momentum, since those are the same thing. Okay, so then finding the impulse for A is just the area under the curve. We just take two triangles and a rectangle and sum them together, and we get 120 Newton seconds. All right. For B, it's just a single triangle, base time 1/2 base times height, 100 Newton seconds. Okay. C, this one's just a rectangle. All right, so it's base times height. All right, and lastly, this one is negative, simply because the forces are negative. So, I do the same base, which is all positive times, because time has to be positive. But if you have a negative force, then you have a negative impulse, which means you have a negative change of momentum. And it's negative 120, because it's the same shape as part A. All right, so that's how we can find the values of change of momentum given a force versus time graph. Okay, but conceptually, the important idea is that the area under a force versus time graph is impulse. Okay, well, here's another similar idea. A particle moves, in this question, a particle moves along the x-axis. Its momentum is graphed as a function of time. All right, so now we have another graph as a function of time, but our vertical axis, instead of being force now, is momentum. Rank the numbered regions according to the magnitude of the force acting in the particle least to greatest. Oh, okay. So last time we were given a graph of force and asked something about momentum, or impulse. This time we are given a graph of momentum and asked something about force. Well, that seems kind of related, doesn't it? Well, it turns out that since change momentum is force times time, then force is change momentum over time, which is to say that force is the slope of a momentum versus time graph. All right? It's just that. Okay. So that means the steepest slope is the greatest force. Well, that must be 1, right? And the least steep is 2. So if we order them, from least to greatest is 2, 3, 4, 1. All right? Because 2 is flat, so there's no force being applied between that point and that point in time. Okay? All right, so cool. Two really neat concepts about graphically how to understand force and momentum. Okay? All right, last example. All right, so this one's about a water wheel. We're going to use that idea of, end collisions, okay, and or a mass flow rate, okay. So it's also kind of a neat engineering application. There's something called a Pelton wheel, and it's shown here. It's kind of diagram, a lot going on, but you really don't care about all of it. So it is a more efficient version of a traditional water wheel. Why is that? Well, the Pelton wheel delivers force to cups. So these are the cups attached to spokes of a wheel, right? That's the wheel part, the water wheel part, by forcing the oncoming water to make a U-turn. And if you think of like an old-timey water wheel, the water isn't being forced to make a U-turn. It's kind of like maybe filling up like a bucket or something, or it's hitting like a blade, and pushing it. But here it's actually being forced to make a U-turn. Like, so the water comes in and it goes back out the exact opposite way, ideally, okay? So if the water is delivered to the wheel at a mass flow rate of 6.5 kilograms per second at a velocity of 28 meters per second, what is the force exerted on each cup of the wheel by the water? Okay, so how would we solve that? Well, we have Newton's third law, so the force on the wheel is equal to the negative of the force on the water. All right, so then the force on the wheel is equal to the negative of the mass flow rate times the change in velocity. Okay, well, the mass flow rate was 6.5 kilograms per second. All right, the final velocity is negative, because I'm just doing the traditional thing and defining to the right as positive x. So that means that the initial velocity is positive 28, okay? And then the final velocity is negative 28, right? Because they got pushed back towards the left in the negative direction. Okay, so then we got a negative times a negative, but a negative here. So that means all the negatives are going to cancel. And, well, they will the next step at least, because I have my negative of my flow rate, negative because of Newton's third law. And then I have my change in velocity is negative, because something was going in the positive direction and gets pushed back in the negative direction. So it's just 28 times 2. So that's a net change in velocity of negative 56 meters per second. But now the negatives cancel, and I have 364 newtons. Why should they cancel? Because I was trying to solve for the force on the wheel. The force on the wheel must obviously be towards the right, which is the positive direction, right? So it's good to make sure the signs work out, and they do, okay? So 364 newtons, the force exerted on the wheel for this particular mass flow rate this particular velocity and the fact that the final velocity was a full U-turn the other way. Okay? All right, so the traditional wheel, on the other hand, is part B. How much more force is delivered by the water using this Pelton wheel than delivered to the paddles of a traditional water wheel where the water is just made to stop, not change direction? Because you still get force by forcing the water to stop. It's still changing momentum, but not as much. Because in that case, V final is 0, see? All right, V initial is still 28, same mass flow rate, okay? Same Newton's third law, so it's the force on the traditional wheel. Well, that's just 182. So if you consider the difference, it's 182. You get twice as much force in an ideal Pelton wheel compared to a traditional water wheel where you're just making the water stop. That's pretty cool, right? So if you need to build a water wheel, build it like that, okay? But kind of neat illustration of conservation momentum. Okay, so that's it for lecture 17. Thank you so much for watching, and check out the subsequent lectures discussing more about momentum.